The first chapter we're going to discuss is effects of current, and the first topic you will learn here is the heating effect of electric current. Suppose I take a conductor, this one is a conductor, and I have applied a potential difference between the two ends of the conductor. So what happens, the first thing what happens when I apply a potential difference is the electrons which are present inside the conductor, the free electrons, they begin to move immediately from the low potential end to the high potential end. মানে যিকেইটা ফ্ৰী ইলেক্ট্ৰনছ আছে কণ্ডাক্টৰ ভিতৰত যেতিয়া আমি পটেনচিয়েলটো প্ৰভাইড কৰোঁ সেই ইলেক্ট্ৰনছবোৰ মুভ কৰিবলৈ লয় from the lower potential end to the higher potential end. And because of this movement, because when they start to move, ki hoy, the atoms which are present inside the conductor or the ions which are present inside the conductor, these electrons and these atoms or the ions collides, mane yoti khunda khai. And এই যে খুন্দা খায় তেতিয়া ইলেক্ট্ৰনছবোৰ যেতিয়া খুন্দা খায় সিহঁতে যাবলৈ এটা বাধা পায় আগুৱাই যাবলৈ এটা বাধা পায় এণ্ড সেই বাধাটোকে আমি কি বুলি জানো ৰেজিষ্টেন্স বুলি আমি জানো ৰেজিষ্টেন্স মানে বাধা the conductor resistance to hold electrons কেটা যাবলৈ যেটো বাধা দিছে হেতু and there is also another point when the electrons moves it has got some kinetic energy electrons bur jehetu move kori ase hetor eta kinetic energy ase and when they collide when collision happens tetia ki hoy hetor kinetic energy to some part of that kinetic energy is converted into heat energy ho ulai jay electrons or kinetic energy to because of the collision heat energy le convert hoy and that is nothing but the heat evolved the heat generated by the conductor and this whole phenomenon is called the heating effect of electric current and also which is known as Joule heating because this phenomenon was originally studied by a scientist named Joule in the year 1841. So there are mainly three laws of Joule's which are known as Joule's law of heating and the first law is the laws of current. The laws of current states that the amount of heat H which is generated in a conductor of resistance R, here I have drawn a conductor, the resistance is R, the current flowing through the conductor is capital I and the amount of time in this process is denoted as small t and here the laws of current states that the amount of heat H which is generated by the conductor of resistance R is proportional to the square of the current or logot heat generated to proportional hoye ase when R and T are constant resistance aru time to jetia constant thake H is proportional to I square that is the laws of current. The second one is the law of time which states that the amount of heat H that is generated in a conductor of a given resistance R is proportional to the time for which a given current passes through the conductor, which is very simple because jiman time current to pass hobo himane besi heat release hobo, which is very obvious. The third is the law of resistance. The law of resistance states that the amount of heat generated in a conductor is proportional to the resistance R of the conductor when a given current I passes through it for a given amount of time small t. Mane capital H is proportional to capital R, the resistance of the conductor. So if we combine this all the three equations, then we can write as H is proportional to I square and the resistance R and also the time t. This one is the main equation and this is also the H is also known as the this is the heat generated in the process and which is the nothing but the work done to a whole jikhini kaam hoise etu ki hoise heat generate hote hoise so we can also write work done W is also equal to I square RT and when we replace this proportionality sign with the equal sign then there comes a constant. At a constant I have which is here J which is known as the Joule's mechanical equivalent of heat. This J constant is known as Joule's mechanical equivalent of heat and the value of J is 4.2 joule per calorie. So now we know that the Joule's law of heating states that the heat generated by any conductor is equal to I square RT and now we need to prove it. So to prove it, first of all, we have to write the Ohm's law as we know that Ohm's law states that V is equal to IR. We write it as equation 1 and by the definition of electric current we know that by definition of electric current, we know that I is written as the charge flowing per unit time. So from here we can write Q is equal to the current into the time taken for the charge to flow. This is written as the second equation. And now we know that the potential difference V is written as W by Q. That is, the potential is the ratio of the work done with the charge flowing. So from here we can write the work done is equal to V into Q. And from equation 1 and 2 we can replace the value of V and Q here. So we get the work done W is equal to I into R into I into T. So from here we get the work done is equal to I square into R into T. Okay, so here the work done is nothing but the heat produced by the conductor. So we can just simply replace W by H. So we can write H is also equal to I square into R into T. Let us now solve some numericals. The first question is, calculate the current flowing through a heater rated at 2 kilowatts when connected to a 200 volt DC supply. So here we are provided with the power of the heater, which is 2 kilowatt, and also we are given the volt, that is the voltage, which is 200 V. So we will write here we are given the power is given as 2 kilowatt, so we can write it as 2 into 10 to the power 3 watt, and the voltage V is given as 200 volt. We need to find the current flowing through the heater. As we know that electric power is equal to voltage into current, so I will be equal to power divided by voltage. So just we have to divide it, power divided by voltage. So it will give us 10 ampere. The next numerical is, there are two resistances given, 60 ohm and 40 ohm, which are connected in series, and if the two resistance are joined to 200 volt means what amount of heat will be developed in each of the resistance in 30 seconds. So first of all we'll have to find the total resistance here. The total resistance here will be 60 ohm plus 40 ohm because they are connected in series, which is equal to 100 ohm. Then we are given the voltage, so you have to find the current passing through the two resistance. The current I will be given by V by R. The voltage is given as 200 volt and the resistance is 100 ohm. So we find that the current flowing through the two resistance is 2 ampere. So now you have to find out the amount of heat that is developed in each of the resistance. That is separately protective resistance heat amount of heat generated to uliaba lage. The first we will find out the heat generated in the 60 ohm resistance. The heat developed in 60 ohm resistance, let me write it as H1, that is equal to I square RT, but you just have to divide it with the joules mechanical equivalent of heat. I square value to whole 2 ampere, resistance to whole 60 ohm, time is given 30 seconds and divided by J value, which is 4.2. A value to uliaba, and the unit of heat will be calorie. Okay, do this calculation on your own. And next is you have to find the heat developed in the 40 ohm resistance. Let me write it as H2. Similar process, I square RT divided by J. I square to whole 2. Resistance is 40. Time is given 30 seconds divided by 4.2. Calculate this amount and the unit of heat will be generated will be calorie. So this amount is the heat generated in the 60 ohm resistance and this one is the heat generated in the 40 ohm resistance. The next thing you have to learn is what is electrical power and what is electric energy. First, the electric power. Electric power is defined as the rate at which an appliance converts electric energy into other forms of energy. Mane, electric power is the rate at which an appliance mane any electric device এটাই কিমান ৰেটত ইলেক্ট্ৰিক এনাৰ্জিটো লৈ আদাৰ ফৰ্ম অফ এনাৰ্জিলৈ কনভাৰ্ট কৰে মানে ইদাৰ হিট দিয়ে নহলে লাইট দিয়ে বা এনি কাইণ্ড অফ এনাৰ্জিলৈ কিমানটো ৰেটত কনভাৰ্ট কৰে সেইটোকে আমি কওঁ ইলেক্ট্ৰিকেল পাৱাৰ. Electrical power is denoted as P is equal to VI, that is power is equal to voltage into current. The SI unit of electric power is watt, and 1 watt is given by 1 volt into 1 ampere. There are other bigger units of electric power such as kilowatt and megawatt denoted like this. And there is another commercial unit of power which is known as horsepower, written as small h and small p. And 1 horsepower is equal to 746 watt. Remember that 1 horsepower or horsepower is the unit of the commercial unit of power. Mane jitu amar electricity bill ahe or amar electric meter jitu unit ahe electricity power or hetu horsepower ahe aru watt nahe. Okay. So next is electric energy. Electric energy is defined as the total amount of work done by the current in a given time. It is simply denoted by the work done. W is equal to P into T, that is the power into the time, the given time, which can also be denoted as I square RT because ami agote poisu work done in a given conductor where current is flowing is given by Joule's law. De ami paisilu W is equal to I square RT, that is simply known as the electric energy. The SI unit of electric energy is joule, and 1 joule is given by 1 watt into 1 second and also can be denoted as 1 volt into 1 ampere into 1 second. The Seebeck effect is a thermoelectric phenomenon which was discovered in the year 1821 by a German physicist named Thomas Johann Seebeck. In the simplest term, the Seebeck effect is the conversion of thermal energy into electrical energy. And to elaborate this effect, let me consider an aluminum rod which is heated at one end and cooled at the other end. The point is to create a temperature difference between the two ends of the metal. Okay, so now the electrons in the hot end or the hot region will possess greater velocities because they will have greater energy than the electrons in the cold region. So consequently, there will be a net diffusion of electrons from the hot region towards the cold region, which will result into accumulation of electrons in the cold region and leaving behind of positive metal ions in the hot region. Okay, so this temperature gradient delta T will result in the generation of an electric field, and that electric field will oppose the further movement of electrons from the hot towards the cold region, and this will lead to development of a voltage delta V across the two ends of the metal, or here the aluminum rod, with the hot region with the positive potential and the cold region with the negative potential. So this potential delta V, which is generated across a piece of metal due to a temperature gradient delta T, is called the Seebeck effect, and the factor which gives us the magnitude of this effect is called the Seebeck coefficient or the thermoelectric coefficient. And mathematically, the Seebeck coefficient is given by S is equal to dV by dt. It can also be written as the difference of the voltage between the hot and the cold region divided by the temperature difference between the hot and the cold region. And from here we can write the delta V, which is the voltage generated across the two ends of the metal, is equal to the Seebeck coefficient multiplied by dt. Let me write it as equation number 1. So now, if I take two different wires and suppose this is a wire made of metal A and this is another wire made of metal B, and I maintain the two junctions at different temperature. Suppose this junction is made hot and this junction is made cold, then the EMF which is generated across the wires will be given as, the EMF generated will be written as VAB is equal to delta V which is generated across the wire A minus delta V of the wire B. Okay, so this VAB can also be written as integration from T0 to T, which is the initial to the final temperature, Seebeck coefficient of A minus Seebeck coefficient of B into dt, because from equation 1 we know that delta V is equal to S into dt, so we can replace it here and we will get the expression for the EMF generated across the wires. Alright, so Seebeck, after studying the properties of some pairs of metals or different pairs of metals, he arranged them in a series which is called the thermoelectric series, and the direction of the current at the hot junction, at this junction, is always from the metal which occurs earlier in the series towards the metal which comes later in the series. Say for example, this wire A is made up of copper Cu and this B metal is say iron Fe. So here at the hot junction, the direction of the current will be from copper to iron, because the metal copper comes before iron in the thermoelectric series. Alright. A very important property of the Seebeck effect is that if we interchange the hot and the cold junction, that is, if I make this junction cold and the cold junction I will make it hot, we are interchanging the two junctions, then the direction of the current will reverse. Now the direction of the current reverses, and hence the Seebeck effect is called reversible process. Now, coming towards the applications of Seebeck effect, the Seebeck effect is utilized in thermocouples, which is a thermoelectric device composed of at least two different conductors or semiconductors. It is used for measuring the temperature difference or the rise in temperature by converting the voltage into its corresponding temperature. It is also used in thermopiles, which is a device composed of a number of thermocouples linked in series or parallel connection to acquire usable voltage. Another use of Seebeck effect is in power generation. Large machines that put out waste heat can use a thermoelectric generator to boost efficiency by turning the heat energy into electricity and putting it back into the system. In my previous video, I have discussed the Seebeck effect, where a difference in temperature created a potential difference or a thermoelectric EMF, and here in this video I will be discussing the Peltier effect, which is just the reverse of the Seebeck effect. That is, here a potential difference will create a temperature difference. In the year 1834, a French scientist named Jean Peltier discovered that when electric current passes through a circuit which consists of two dissimilar metals, heat is evolved at one junction and heat is absorbed at the other junction, and that is what is called the Peltier effect. So if we take a thermocouple made of copper and iron, and if we now connect a battery here, then current will be flowing from the positive towards the negative terminal of the battery. And here, this is the junction, say I will name it J1, and this is the junction J2. So where the current, this junction J1, where the current flows from iron to the copper, iron towards copper, this junction was found to be liberating heat, so this junction was found to be hot, and the other junction where the current flows from copper towards iron, here it is found that this junction absorbed heat, and so the junction was cold. Okay, so now let's try to understand the reason behind this effect. Okay, we all know that there is a large number of free electrons present inside a metal, or say conductor or semiconductor. So if we join two semiconductors or conductors, for example, I'll take the same example. For one is copper, the other is iron. So those free electrons will diffuse from the one side where there is large number of free electrons per unit volume towards the side where there is less number of free electrons per unit volume. Okay, so in the case of copper and iron contains much more number of free electrons per unit volume than copper. So obviously the electrons will diffuse from iron towards copper. Okay, so after diffusion, iron will be left with a positive charge because it has lost those free electrons, and copper will be left with a negative charge because it is gained those extra free electrons. Or we can say that iron is left with a higher potential than copper. Okay, so I'll write it here. Iron is at a higher potential, a positive potential, and copper is at a lower or a negative potential. Okay, so now let's get back to some very basic concept. Okay, we all know that electrons which are negatively charged are always attracted by the positive terminal of a battery. This one is the negative terminal, this one is the positive terminal of a battery, and the electrons will be always attracted towards the positive terminal of a battery. And we also know that electric current flows in the reverse direction of the flow of electrons. So electric current flows from positive towards the negative terminal of a battery. Or we can also say that electrons always flows from a lower to a higher potential, and current always flows from a higher to a lower potential. Okay, and we also know that energy of an electron is denoted by E is equal to minus QV. And from this equation, it is obvious that when potential will increase, energy will decrease. Okay, so here when the electrons are traveling from a lower to a higher potential, the potential is increasing. So when the potential increases, the energy has to decrease. So let us put this concept here in junction J1. What will happen in the junction J1? The current is flowing from a positive to the negative potential. Okay, so means the current is flowing from a higher to a lower potential. So here in this case, in junction J1, potential is increasing, so the energy has to decrease. The energy decrease implies that energy is being liberated. So when the energy is liberated, this junction will automatically get hot. Okay, so now let's look at the opposite case. Okay, if this is the positive terminal, this is the negative terminal of the battery, and if I make this electron flow in the reverse direction, that is from the positive towards the negative potential, which is not the natural way, then I have to do some work. I have to put some extra energy in moving the electron from the positive towards the negative side. Okay, or from flowing the current from the negative towards the positive side. Or we can say that when electrons flow from higher to lower potential, or current flows from lower to higher potential, some energy must be given, some energy will be absorbed. So if we put this concept here in junction J2, what's happening? The current is flowing from a lower to a higher potential, from a negative to a positive, that is from a lower to a higher potential. So in this junction J2, heat will be absorbed. Heat will be absorbed, so this junction will get cooled. Okay, so like in Seebeck effect, if I reverse the current flow, if I reverse the direction of the current, the both junction will be interchanged. Okay, so Peltier effect is also a reversible process like the Seebeck effect. Applications of Peltier effect. Peltier elements are commonly used in consumer products. They're used in cooling electronic components and small instruments. The cooling effect of Peltier heat pumps can be used to extract water from the air in dehumidifiers. The Peltier effect can be used to create a refrigerator that is compact and has no circulating fluid or moving parts. Thermoelectric coolers can be used to cool computer components to keep temperatures within design limits or to maintain stable functioning. A Peltier cooler with a heatsink or water block can cool a chip to well below ambient temperature. topic is Thompson effect. There are two types of Thompson effect, positive Thompson effect and negative Thompson effect. Let us first look into positive Thompson effect. Here I have taken a copper bar, more than copper bar named AB, and C is the midpoint of the copper bar, and I have provided heat in the midpoint C. So what I will find out that heat is getting absorbed in the portion A to C and heat is getting evolved in the portion C to B. মানে heat A to C portion not absorb hobo mane heat to heat anibo aru C to B portion not heat to evolve hobo mane conductor dale heat eribo, and we see that the direction of current is from in the conductor is from A to B, and also the heat transfer is from the portion A to point B. So here we find out that the heat is getting transferred due to the current flow in the direction of the current, and this is known as positive Thompson effect. And this effect is shown by metal like copper, silver, zinc and cadmium. The next is negative Thompson effect, which is the inverse of positive Thompson effect. Here I have taken an iron bar named AB, and similarly in the same way I have named the midpoint as C, and I have provided heat in the midpoint C. Here in case of iron bar we will find out that in the portion A to C heat is getting involved, meaning heat to A portion, and from the portion C to B heat is getting absorbed, মানে heat transfer to from point B to point A. That is, the heat transfer direction is in the opposite direction of the current flowing through the conductor. So in this case the Thompson effect is called as negative Thompson effect, and this phenomenon is observed in metals like platinum, nickel, cobalt, mercury and iron. The next chapter of Unit 5 is Chemical Effect of Current. Here we will learn that when an electric current flows through a conducting solution, then chemical reactions takes place in that solution. মানে যেতিয়া electric current এটা flow হয় through a conducting solution, এটা solutionৰ মাজেৰে যেতিয়া electric current pass হয়, then there is chemical reaction which takes place in the solution. Chemical reaction হয় যিটো কাৰণে the molecules of the solution gets dissociated. যিবোৰ molecules আছে solutionটোৰ এইবোৰ ভাঙি যায় আৰু ভাঙি molecular পৰা সিহঁতি ion হৈ যায়. Okay. Now, the passage of electric current through liquids is different from conductors. When current flows through liquid, it is always associated with some kind of chemical change. For example, if current flows through a solution of acid in water, suppose current flows through a salt solution, like here I have taken sodium chloride solution, it is a salt solution, and or it can flow through base, then some chemical effect is seen, and this is what is known as the chemical effect of electric current, which was first observed by Michael Faraday in 1833. Now, let us see what is electrolysis. The whole process of decomposition or dissociation of compounds in a solution which due to the passage of electric current is known as electrolysis, and the solution which undergoes the electrolysis process is known as electrolyte, and the process of electrolysis is carried out in a vessel. যিটো electrolysis হ'ল the process of electrolysis যিটো ভেসেলত আমি কৰো, যিটো ভেসেলত হি হয় সেই ভেসেলটোক আমি কি বুলি কওঁ electrolytic cell or voltameter. Here in a voltameter there are two metallic plates. You can see two metallic plates here. These are known as electrodes, by which the current enters and leaves the electrolyte, and they are known as electrodes. There are two electrodes. One is named as A, which is known as anode. One is named as C, which is called the cathode. So what happens here is a source of EMF is connected across the two conducting plates which are dipped into the electrolyte. The plate A, which is connected to the positive terminal of the battery, is called the anode, and the plate C, which is connected with the negative terminal of the battery, is called the cathode. And the whole process of electrolysis is based on the ionic theory or the theory of electrolytic dissociation, according to which the molecules of the electrolyte breaks up into two parts which are called ions. Here I have taken sodium chloride solution. So ইয়াত কি হ'ব, যেতিয়া sodium chloride solutionৰ মাজেৰে current pass hobo, electric current pass hobo, then this NaCl molecule will break up into two ions, sodium and chloride. Here sodium is positively charged ion and chlorine is the negatively charged ions, and these two ions are oppositely charged with equal electric charges, and these two ions are held together by the electrostatic force, which is given by F is equal to 1 by K, Q1 Q2 by R square. And here Q1 and Q2 are the charges of both the ions, and K here is the dielectric constant of the medium. There are two laws of electrolysis which are known as Faraday's law of electrolysis. The first law here states that the mass of ions which are liberated by a current in the process of electrolysis is proportional to the quantity of charge which is passing through the electrolyte. Here M is the mass of the ions that is liberated in the process of electrolysis, and Q is the amount of charge which is passing in the process of electrolysis. And we know that Q can be written as current into time. So when we replace Q by IT, we can write the mass of the ion is proportional to current into time. And when we replace the proportionality sign with an equal sign, there comes a constant which is here Z, and Z is known as the electrochemical equivalent or ECE of the material. And electrochemical equivalent of an element is defined as the atomic weight of the element divided by the valency of that element. The second law of electrolysis states that if the same current passes through different electrolytes for the same time, then the masses of different ions deposited at each of the electrodes are proportional to their chemical equivalent. That is, here M1 and M2 are the two different types of ions which are deposited at each of the electrodes, and E1 and E2 are the electrochemical equivalents of the two different types of electrolytes. So from the first law, now we can state that M1 is equal to Z1Q. That is, here we've seen that M is equal to ZQ. So we can write for the first type of ion, M1 is equal to Z1Q, and for the second type of ion, M2 is equal to Z2Q. Therefore, we can write, if we divide M1 by M2, we will get Z1Q by Z2Q. We can cancel out the Q term, and then we get M1 by M2 is equal to Z1 by Z2, and we have named it as equation 2. So if you see equation 1 and 2, the left hand side of both the equations are the same. So we can write what? E1 by E2 is equal to Z1 by Z2. So just replace, you take E2 here and bring Z1 here. So we see that E1 by Z1 is equal to E2 by Z2. So we have seen what? E by Z is a constant. It doesn't changes. So we can, here we have denoted E by Z as a constant F, and here F is called as a Faraday. The second law of electrolysis states that if the same current passes through different electrolytes for the same time, then the masses of different ions deposited at each of the electrodes are proportional to their chemical equivalent. That is, here M1 and M2 are the two different types of ions which are deposited at each of the electrodes, and E1 and E2 are the electrochemical equivalents of the two different types of electrolytes. So from the first law, now we can state that M1 is equal to Z1Q. That is, here we've seen that M is equal to ZQ. So we can write for the first type of ion, M1 is equal to Z1Q, and for the second type of ion, M2 is equal to Z2Q. Therefore, we can write, if we divide M1 by M2, we will get Z1Q by Z2Q. We can cancel out the Q term, and then we get M1 by M2 is equal to Z1 by Z2, and we have named it as equation 2. So if you see equation 1 and 2, the left hand side of both the equations are the same. So we can write what? E1 by E2 is equal to Z1 by Z2. So just replace, you take E2 here and bring Z1 here. So we see that E1 by Z1 is equal to E2 by Z2. So we have seen what? E by Z is a constant. It doesn't changes. So we can, here we have denoted E by Z as a constant F, and here F is called as a Faraday.